Hey everybody, in this video we're going to talk about some special right triangles. And they're special because they're used really frequently when we get into the thick of trigonometry. We use these relationships for these right triangles quite frequently. So that's why we call them the special right triangles. So let's start with this one on the left. We've got a right triangle here, and this is a equilateral right triangle. We can see that the right angle is at the peak. So the two sides are equal, the two legs are equal, which also means that the base angles are also equal. That's our equilateral triangle. Basic definition of equilateral triangle. So what are the measurements of these base angles? Well, if 90 degrees are taken up for the right angle, that means we've got 90 left for the other two. And if it's an equilateral triangle, they have to be the same. So if we just divide that by 2, we get 2 angles of 45 degrees. Now, this one we call as a 45, 45, 90 triangle. It's a kind of a silly name, but that's what we call it, 45, 45, 90. So what we're going to do is we're going to look at the relationship of the sides of these things with the angle. We're going to look at sine, cosine, and tangent with this. So if we call this side, let's just say we call this measurement 1 unit, whatever that is, 1 foot, 1 meter, whatever you want to call it. We're going to just call this unit 1 unit. So if that's 1 unit, then clearly this other side has to be 1 unit. And we need to find out what side C is. Now I picked side C because that ties in with our Pythagorean theorem. And I know it's opposite the right angle, so that's the hypotenuse, and I know the hypotenuse in the Pythagorean theorem is C, so I pick C. You can pick X, you can pick any letter, it doesn't matter. All we're trying to do is figure out what this length is. So if I just plug in the values that I have in the Pythagorean theorem, I've got 1 squared plus 1 squared equals C squared. Do some simplifying, and we get 2 equals C squared. So when we take the square root of that, C is going to equal the square root of 2. So now if we want to look at sine, cosine, and tangent of these values, remember our sine of 45 degrees, so we don't use 90 degrees when we do sine, cosine, and tangent. We use 90 degree triangles, right triangles, but we don't reference the sine, cosine, and tangent from the 90 degree angle. We always do it from the other angles. Okay, so sine of 45 degrees, if you remember, sine is opposite over adjacent. So if we look at that 45 degree angle, that's going to be 1 over the square root, I'm sorry, did I say opposite over adjacent? Opposite over hypotenuse, excuse me. 1 over square root of 2. Now, a lot of mathematicians consider it bad form to keep a square root in the denominator. So what we're going to do is we're going to multiply this by square root of 2 over square root of 2. We're not changing the value of this, because we're multiplying 1 over square root of 2 by 1. That 1 is just square root of 2 over square root of 2. Remember, anything over itself is 1. But what that does is when we multiply these two things across now in the denominator, square root of 2 over square root of 2 times square root of 2 equals 2. So that gets rid of that square root in the denominator and just kind of pops it up in the numerator. There's the reasoning is you can't really divide something by an irrational number. So what we're doing this way is we're now taking a whole number and dividing an irrational number by that. So that's kind of why we do this. But like I said, it's just kind of considered bad form by a lot of mathematicians. So what we do is we rationalize it, like I said there. Okay, so tangent there. So let's go to a side tangent, I should say, not cosine tangent. Anyway, I digress. So let's go to cosine. Cosine of 45 degrees. So cosine of 45 degrees is going to be adjacent over hypotenuse, which again is 1 over square root of 2. We rationalize it just like we did in the purple here, and we get square root of 2 over 2. All right, and then finally tangent of 45 degrees is going to be opposite over adjacent. So we're going to have 1 over 1, and obviously simplify that to 1. So these are 3 real key relationships that you should probably get to know and be familiar with, or at the very least know how to find quickly. If you're not in the memorizing game, which a lot of people aren't, and that's fine, you should be able to reason your way into how these values were found the same way that we just did here. All right, so for our second right triangle, we're going to look at this one on the right. And if you notice, this actually isn't a right triangle. This is an equilateral triangle where we've got all of our sides the same and all of our angles the same. So there's nothing right about this so far. But if we drop the height or sorry, I'm getting ahead of myself. So we know our angles are 60 degrees, but if we drop this height down, or the altitude of the triangle, from the peak of one vertex or one angle to the other side, that creates a 90-degree angle. And that kind of cuts our triangle into two. So if we know that this is 60 degrees, then the other one, the top angle, has to be 30 degrees because it's cutting that angle in half. So we call this triangle our 30, 60, 90 triangle. All right, so it comes from an equilateral triangle. So this is where our second special right triangle that we're going to look at. So let's pull this one out on its own, and we've got our 30, 60, and 90 here. So we need to set up some units with this. So let's call this side 1 unit. Again, whatever that unit might be, whatever that unit of measurement might be, we're going to call that 1. And if we go back to our original equilateral triangle, that would mean that this part here was 1. So if that's 1, that's half of the whole side. And we said that the whole side, if they're all the same, if that's half of that, that means that this measurement is 2, that each side is 2. So if we cut it in half, that's 1, right? So our hypotenuse of our special triangle is going to be 2. So we've got 1 and 2, and now we need to figure out what this other side is, one of the legs. So I'm going to go back to the Pythagorean theorem again. You could, I'm going to use 1 squared plus b squared equals 2. Again, you could use a squared plus 1 squared. It doesn't really matter, just as long as you recognize that it's a leg, it should be on the left side of the equation, or on the plus side of the equation if you'd like. So we're going to do some basic calculations here. Move that 1 to the other side, get b squared equals 3. So b is going to equal the square root of 3. So now, when we start looking at these relationships, let's start with sine of 30 degrees. So sine of 30 degrees, again, sine is opposite over hypotenuse. SohCahToa, opposite over hypotenuse. So we're going to go to the opposite side, 1 over 2, because the hypotenuse is 2. So there's our sine of 30 degrees. Sine or cosine of 30 degrees. We're going to do our adjacent over hypotenuse. So that's going to be square root of 3 over 2. And finally, tangent of 30 degrees, opposite over adjacent. So 1 over square root of 3. Let's rationalize that like we did with the purple, and we're going to multiply that by square root of 3 over 3, and it becomes root 3 over 3. So there's our 3 values for the 30-degree angle. But we also have the 60-degree angle. So sine of 60 degrees. So take a second if you haven't already figured it out. Maybe pause it, look at the relationship, see if you can come up with it. So sine of 60 degrees, we're going to take opposite over hypotenuse. So that's going to take the square root of 3 over 2. Cosine of 60 degrees, we'll take the adjacent over hypotenuse. So that's 1/2. And tangent of 60 degrees is opposite over adjacent, root 3 over 1, or square root of 3. And you might notice some of these values kind of switch. The sine and the cosine. Sine of 30 is the same as cosine of 60. Cosine of 30 equals sine of 60. You'll start seeing a lot of these patterns kind of popping up. But these 6 are also real key values to keep in mind and remember, or be able to reference and get back to, because we use these a lot in trigonometry. Now, the thing to keep in mind, another thing to keep in mind, there's lots of things to always keep in mind, but the thing to keep in mind is when you look at these square roots, don't think that automatically, the square root is the hypotenuse, because over here in our 45, 45, 90 triangle, the square root term or value was the hypotenuse. That's not the case in the 30, 60, 90 triangle. Recognize that the square root of 3 is a leg. So what you really want to consider is that that the hypotenuse is always the longest measurement of a right triangle. So if you think about what the square root of 2 is, that's bigger than 1. That's actually, I think it's like 1.414, and it's an irrational number, so it goes on forever. But that's bigger than 1, clearly. So that's going to be our hypotenuse. And similarly, if you look at the square root of 3, which is, I think, 1.7 something, 1.73, and again, another irrational number that goes on forever, that's between 1 and 2. So that's not going to be the biggest value of our right triangle, our 30, 60, 90 triangle. So 2 will be the hypotenuse. So that's a good thing to keep in mind as you're trying to set these relationships up, or if you're just trying to fill them in so that way you've got a reference on a piece of paper or something. Just make sure that you don't fall into some of these traps. But these are values that you're going to come to know and love. Hopefully this helps you kind of understand where everything came from, and I'll talk to you in the next one.